Hello everybody, I'm Captain Mam again. I'll start off from where I left last time about the PZX triangle. This is the Earth with the poles, observer, and the equator. And you can clearly see that the observer is north latitude. Celestial sphere, projecting the poles onto the celestial sphere, your elevated poles or celestial poles. And the point overhead, the observer is zenith. Equinoctial, projection of equator onto the celestial sphere 90 degrees to the celestial pole. Meridians we know are semi-great circles, so the meridian of an observer is where the meridian observer is. So the observer's meridian is P, Z, Q, P dash, and this side is the observer's inferior meridian, because we know that part semicircle, semi-great circle forms another meridian. 90 degrees from zenith, all points, rational horizon. Now here the rational horizon we name the north, south, east, west of the rational horizon. We do not bother about north-south of the celestial sphere because all our now calculations will be based on the horizon system, in which we'll be talking about the altitudes and the azimuth. So the point closest to the pole is named accordingly. Here this point is closest to North Pole, so we call it as the north of the celestial pole. Going clockwise, the next point would be east, continuing further south and then west. Now, rational horizon being a great circle, the plane would be passing through the center of the sphere, that is the center of the Earth, and it's 90 degrees or right angle to the radius of the observer here. So, this rational horizon is dividing the celestial sphere into hemispheres, north and south. You can see north here and south here. One containing the zenith or the observer here is the visible hemisphere. So all the bodies which are here on top will be visible to us. The one below the rational horizon, we cannot see anything. So only bodies which are there on the visible horizon will be visible to us. And a great circle passing through zenith and nadir, your vertical circle. And this is a figure on the observer's meridian as the Earth and the celestial sphere would look if it was being viewed from the west. And being viewed from the west, I will not be able to see east because it's on the other side. So I'll just get rid of east here. Now here I am making this diagram with pole on top. Observer's meridian, as I said, 90 degrees to the poles is the equator, equinoctial. And observer being north of the equator, observer latitude north. Observer's meridian, the side observer is, the other side is your inferior meridian. 90 degrees to zenith, rational horizon. And you name the points as north, closest to North Pole, going clockwise east, south, and west would not be visible to me because west is on the other side of it. So this is a figure as I'm seeing it from the east. Let's have a body, celestial body with the north declination. A celestial meridian passing through the body. And we know the definition of declination is the arc of the celestial meridian. This is our declination. From pole to the equator is 90. So from pole to the body, 90 minus declination, and we call it as a polar distance. Vertical circle through the body. Vertical circle is passing through, joining the zenith and other, and altitude is the arc of the vertical circle. Zenith to rational horizon is 90, so Zx is 90 minus altitude, and we call it as zenith distance, Zd. Pole to equator 90, pole to zenith latitude remaining is 90 minus latitude. Azimuth is the angle at the zenith contained between observer's meridian and the meridian and the vertical circle passing through the body here. Azimuth is named east or west of the meridian. The meridian is here and I'm looking at east. So the azimuth would be northeast in this case. Angle P we call it as LHA. Of course in this case it is not LHA because LHA is measured westward from the observer's meridian to the body. So in this case your LHA is from your meridian to the body. And as you can see it here, it is more than 180 because starting from here is up to this place is 180 and then plus. So when the body is on the east, as you can see, I'm seeing the east side of the horizon, LHA is always more than 180 degrees. Now this, I've just changed this figure here. Instead of having pole on top, I've just made the zenith on top. 90 degrees is the rational horizon. Now whatever your latitude is, accordingly I've placed my pole here. And again, observer north. The naming of your rational horizon closest to north pole, north going clockwise east, which will be on the other side of the screen here, so I'll not be able to see east. Then I'll have west, south, and then I'll have west. So this figure, what I'm showing you is as seen from the west. We are seeing the rational horizon, the west side. I've taken here a body with the southern declination. Declination is arc of the meridian. And now PZ, PX would be 90 plus declination here. And that's the polar distance. Vertical circle through the body, and arc of the vertical circle is your altitude. And Zx is 90 minus altitude, Zener distance. Angle Z, your azimuth. PZ was 90 minus latitude. Angle Z is your azimuth. And now you're seeing the body towards the west. And as I said, named it your meridian. Here, measured east or west of the meridian and named from the elevated pole. Elevated pole was north. I'm seeing the west. The azimuth here will be northwest. Angle P, as I said, was LHA, and in this case, you are measuring this angle west clockwise. So this angle P is our LHA here. So when I'm seeing the west, when the body is on the west, then the LHA is less than 180 degrees. There is PZX triangle, P the poles, elevated pole, Z your zenith, X is the body what we are observing. And as you can see, all the 5 parts of this triangle are in use. The only angle what we are not using is angle X. It is not used in navigation and it is called parallax angle. Now why this thing about PZX triangle here? Well, we are interested in navigation to find out our position, and the knowledge of PZX triangle is the one what is going to be important for us to be calculating our latitudes and longitudes. So we should be clear about this PZX triangle here. Now on the observer's meridian again, equinoctial, zenith, observer north, and the side your zenith is, that is your meridian, observer's meridian, the other side is inferior meridian. Equinoctial and a celestial body on the observer's meridian. And knowing the altitude of a body on your celestial meridian, we can find out our latitude. So how do we go about calculating our latitude? Once if we know our altitude of a body when it is on our meridian. So z to x is our altitude. It can't be on the other side because the other side is more than 90. Altitude can never be more than 90. So x to n is not altitude. Altitude will be always less than 90. X s 90 minus altitude, zx, Zener distance. Declination from equator to the body, ux. So if I know the altitude, I know the declination, I can find out my latitude. Here, declination plus Zener distance is my latitude. In this case, you notice that the declination and the latitude are the same name. The declination is less than the latitude. The second scenario which is possible is that you have a body on your meridian. Here, your declination is more than your latitude. Your latitude is qz and the declination is qx. Now, my altitude, if I know my altitude, that is xn, that is my altitude, then xz becomes my zenith distance, q to x is my declination, declination minus zenith distance, declination minus zenith distance would give me qz, that's my latitude. The third case, I've taken a body with southern declination. Altitude when it is on the meridian, x to s, z to x, altitude minus 90, zenith distance, q to x, my declination south, and zenith distance minus the declination, I will get qz, that is my latitude. Now to find out my zenith distance, I would require my altitude. To find out the declination, I'll require the time. The true altitude what I require to find out my zenith distance is the arc of vertical circle above the rational horizon. Rational horizon is a great circle. Its plane must be passing through the center of the sphere. In this case, we are talking about Earth. It should be passing through the center of the Earth. But an observer can never be at the center of the Earth. He's at the surface. So some corrections would have to be applied to whatever what I'm observing as the altitude, to be able to get the values at the center of the Earth. At sea, we use a sextant for measuring the altitudes, the vertical angles, and the horizontal angles. The altitudes are the vertical angles. Sextant As an instrument, it's possible to have some errors, and the important error what we'll be talking about is the index error. Index error is either on or off the arc. If it is on the arc, then you subtract it from the reading of the sextant, and if it is off the arc, you add it to the reading of the sextant. Now, observer at sea level, his vision will be limited to the curvature. As soon as the earth starts curving, he will not be able to see anything further than this. So it will be limited to the curvature, and this is what is his visible horizon. At sea, we will not be on the surface of the earth, we are on a ship. Our heights will keep on varying. And if the heights keep on varying, then my visible horizon will also keep on changing. And depending upon whatever height I am on, I will be observing the altitude of this body above my visible horizon. So what I have observed from the body to the visible horizon, that's my observed, taking into account what my index error for the sextant is. The altitude of the body should be at the sea level, because as you see, suppose you are going higher and higher up, you'll be getting a different altitude. But at that particular time, the celestial body would be having only one particular altitude. So it should be at sea level or at eye level. So my altitude should be this angle, x o dash. Whereas what I noticed, what I observed was this, and it should have been x o b dash. S1 o dash is a small circle which is passing through the eyes of the observer. We call it as the sensible horizon, and that is parallel to the rational horizon. And you can see here, this angle is definitely bigger than this angle at sea level. Observed is x o dash b2, but it should have been x o dash s1 or x o b. So this angle o dash angle here are equal, and that is greater by the amount what we call as dip. And dip is the angle between the sensible horizon and the visible horizon. And as you can notice it here, that to have the body onto my eye level or onto my sensible horizon, I should subtract dip. So dip is always subtracted, which is an error due to your height of eye. The higher your height is, the greater the angle of dip would be. So once you applied height of eye correction to the observed, what you get is apparent altitude, and you have got it onto your body, onto your eye level. Now this is what altitude you have got after applying height of eye correction. And this is what we call apparent altitude here. Now we know that a ray of light, when passing from one medium to another, suffers a refraction, that is, as it turns towards the normal, away from the normal. Now in this case, of course, the rays of light are coming from the rarer to denser medium, so they keep on turning towards the normal. And ultimately, what the observer sees is here. Instead of the body being here, what observer sees due to refraction is here. So what he sees is always more than what the actual altitude is. So the effect of refraction would have to be taken into account to get the correct value of the altitude. And as the refraction is making the bodies look higher, you will always subtract the correction for refraction. All the values of declination, GHA, what are given in the almanac, they are all for the center of the body. So, when we are taking a body, sun or moon, we have to be taking up the center of the body. But we cannot make out the center of a sun or of sun or the moon. It doesn't make a difference for stars and planets because they are too small to bother about the centers. They look like tiny dots. So in case of sun and moon, we talk about limbs. So one is the lower limb, which is closer to the horizon. We call it the lower limb. And the one which is further away from the horizon, we call it as a upper limb. Now, if I take the sun or the moon like this and bring it to the horizon, and I bring the one which is closest to the horizon, the lower limb, to get to the center, I will have to add the semi-diameter. And if I was just talking about the lower limb of the sun, then I would have to subtract the semi-diameter to get the center of the sun. In practice, lower limb of sun is always taken into for measurements because we can see full sun. The problem is only with the moon. Because of its phases, we see only part of the moon. So for moon, it becomes important the limbs. So when the moon is in crescent, you see the upper limb, and when it is gibbous, you see the lower limb. So at that particular time, you have no choice other than taking the upper or the lower limb. For sun, always possible to get the lower limb. So we normally talk about lower limb for sun. It's only for moon that upper and lower limb has to be talked about. So now to get the body center, we will have to add or subtract the semi-diameter which is given in the almanac. Now the true altitude, when we define, we said it is on this at the center of the earth. It's the arc of the vertical circle. It's a great circle, so angle will be at the center of the sphere here. This arc and this angle. Now in this case, this sensible horizon, your visible horizon here, is parallel to the rational horizon. So these two are two parallel lines. So this angle here, XAV, is a corresponding angle to XCH. So they both will be equal. So this angle becomes my true altitude. Now if you consider this triangle here, XOA, this angle XAV is its exterior angle, external angle. And we know that the sum of the two internal opposite angles is equal to the external angle here. So apparent altitude plus this angle is equal to true altitude. This angle OXA is called parallax. Parallax is the angle which is made at the center of the body here between observer at the surface of the earth and observer at the center of the earth here. So the true altitude is apparent altitude plus parallax. And as you can see here that this is true is your external angle. So parallax will always be added. So this is how you get your true altitude with these corrections to the observed altitude of the celestial body. Now 90 minus altitude, we get the zenith distance. So now we have got one part of the thing what is required for calculating a latitude. We have our zenith distance. We'll be talking about declination a bit later. Now if we apply sine rule to this triangle COX. Sine rule is what? Sine of this angle divided by sine of this angle. Sine of this angle divided by the side. Sine of this angle divided by the side opposite. So here I have just written down two of them here. Sine parallax and the sine opposite OC is equal to sine of this angle here, XOC or COX divided by CX. I have not bothered about the third angle here. Now just inter cross multiplying here. I have brought the OC here. It's become sine of COX. And angle COX is apparent altitude plus angle 90. This angle COV is 90. So ultimately we get that sine of parallax is equal to cos of apparent altitude. Cos, if the altitude is 90 degrees, cos is 0. So parallax becomes 0. So parallax reduces as the body gains in its altitude and it becomes 0 at 90 degrees. Now the same formula, if you look at it, when cos is the maximum, that is 1 when the angle is 0. If my altitude was 0, then I will have the value 1 here, and at that particular time the parallax would be the maximum, and at that time we call it as horizontal parallax. So parallax is maximum when the body is on the horizon and this angle x O x dash c is the horizontal parallax. Just applying this sine rule again here, XOC. Sine parallax divided by OC, sine of this angle divided by CX, and this is what we had come to, cos of apparent altitude. Now, considering that the declination does not change much, so the body would be moving along this declination circle here. So CX and CX dash would be nearly same. So I can just substitute CX dash for CX here. And this is what I have done here. I have just substituted this. And now what I have got is this triangle here, COX dash. One side is OC is the perpendicular of that, and CX dash is the hypotenuse of this. And that is sine of this angle here, parallax. So now we have got this thing just changed over from sine parallax to sine HP into cos of apparent altitude. Sine is a very small angle, so I'm just getting rid of the sines, and then we just call it as the parallax is equal to HP into cos of apparent altitude. In case of moon, HP is very large because it's very close to us. It is up to 60 minutes. In case of sun, it really doesn't make a difference. But in case of moon, it's a big correction. And as you can see, that with the increase or decrease of the distance from the Earth, from the observer, this will keep on changing. So this is an important correction in case of moon, parallax, in which the parallax has to be calculated with this formula here. As I said, for moon doesn't make a difference, for sun doesn't make a difference because sun's distance really huge compared to what it is moon. Moon is very close. So for moon, the parallax would just change from normal parallax here to HP into cos of apparent altitude. Now, moon is very close to us compared to sun. So, its altitude, with its altitude, even its semi-diameter appears to change. Uh, Semi-diameters, what we talked about, are given in the almanac. They are given as seen from the center of the Earth, but the observer is on the surface. So, for the moon, with the change in altitude, there is a change of declination of the semi-diameter, and the difference, what is between the tabulated in the nautical almanac and what we see, is called augmentation of moon's semi-diameter. The difference between the tabulated and the observed is called the augmentation of moon's semi-diameter. So for case of moon, also there's some additional correction which will have to be applied to semi-diameter here. Now if you look at it here, this is what is given to us in this almanac. This angle here, L, C, and M. Now when the body is at the horizon, it doesn't make much of a difference because you can see that the distances are nearly the same here. So even if it is observed from the center or from here, they're nearly same. So it doesn't make a difference. But as the body approaches up, rises up, goes up high in the altitude. Now this is the angle what is tabulated in the almanac, which is your sine of the angle here, M, C, L dash, which is equal to perpendicular by hypotenuse here. And this is what we observe when we are at the surface of the Earth. Now you can see here that the distance L dash O is less than L dash C. So what you get here is that the sine of this angle M O L dash would be more than the sine of angle at the center of the Earth. So your semi-diameter, what you're observing now when you're at the surface of the Earth, is more than what has been tabulated for you on the almanac. This is the moon which is right overhead. And this is the angle what has been tabulated in the almanac. And this is what you will see. M O L double dash. And you can see here that M O dash is the least possible in the solar circle. And it is right overhead. So at this particular time, the sine of the angle of O there would be the maximum. So your augmentation, what is the difference in the semi-diameter what you observe here, would be the maximum when it is overhead. And as you can see here, that what we are observing on the surface of the Earth, we are always seeing more than whatever is given in the almanac. So this correction of semi-diameter, which is called the augmentation of moon semi-diameter, is always added to the semi-diameter of moon given in the almanac. So for moon, these are the two additional things what we got to remember. The semi-diameter and the parallax has to be calculated with HP. semi-diameter of sun is also varying actually. It is varying from 15.8 to about 16.3 when the sun is closest to the earth and when it is further away from the earth. But that is basically the difference is just about zero point 0.5 minutes, and that is over the period of 6 minutes. It doesn't make a difference in a day when the sun is coming up. So there is no augmentation of semi-diameter for sun, because as you can see here that from 15.8 when earth is the furthest from the sun to 16.3 when it is closest in the month of July, nearly 6 months, just changing about zero point 0.5. So for sun, semi-diameter, whatever is given in the almanac, that holds good for 3 days. Now, this is how we will be correcting our sextant altitudes. If the object was a celestial body was sun, I'll be taking the sextant altitude, applying the index error on and off, plus or minus. Then I get the observed altitude. Then depending upon whatever my height of eye is, I'll always subtract the height of eye correction. That is given on our tables or in the almanac, like this in the form table. After subtracting that, we get apparent altitude. To this, I have to apply refractions. The table for refractions are given in our nautical tables there, Norries and other tables there. You get your refraction corrections from there. And the semi-diameter is given on the page of nautical almanac for the day, and this is a semi-diameter for sun, which is valid for 3 days page here, and this is a semi-diameter for moon, which is given for individual dates here, so 1 to 3 days here. And then the last correction we talked about is parallax. Parallax again from our nautical tables, and as you said, always added. I have always written always added. Similarly here for refraction is to be subtracted, and for dip, of course, it is minus sign. So this is how you get your corrections, individual corrections to the altitudes of a heavenly body. And after applying parallax, you get your true altitude. If it was planet, section altitude, index error, observed, dip, apparent altitude, refraction. There is no semi-diameter there, so we don't apply semi-diameter. Get the parallax, you get your true altitude. For moon, you get the sextant altitude, index error, observed altitude. So this is same for everybody. Apparent altitude, refraction, semi-diameter. Semi-diameter, as I said, is given at the bottom of your nautical tables here. These are semi-diameters for moon. For moon, it is given for 3 days. And then we have to add the augmentation, which I just explained a little earlier. And you get the augmentation from the tables, nautical tables there. And again, if you don't remember, it is written down here, added to moon semi-diameter. So it's always added. You get your semi-diameter. Then comes the parallax after semi-diameter, what we have seen here from semi-diameter parallax. Now for moon, parallax is HP into cos of apparent altitude. You get the HP from the almanac. You go to the date concerned, and whatever time is, here you get your HP. So you get your HP from the nautical almanacs, and then you have your apparent altitude here, and you can calculate your parallax and get your true altitude. For stars, the same thing up to apparent altitude, refraction, Again, no semi-diameter, and you get your true altitude. So this is how you go about solving for corrections for sextant altitude. Of course, these are all individual corrections. You are just to be aware of it. It's a principal thing. Sometimes can be asked. Though in practice you don't use it, we use total corrections instead of parallel. So we use total corrections. So we calculate apparent altitude. Then we use total correction. If you look into your almanacs, you'll see that there's a page for total corrections here for sun, stars, and planets. With of course additional correction for the planets here, Venus and Mars. So these are the corrections what you'll be applying instead of the refraction, semi-diameter, and parallax. Life is made easy with the help of total correction. And applying this according to whatever it is, lower limb, upper limb, for sun and moon, months are there. Of course, for stars and planets, there's no limb. So all the corrections negative here, and you get your two corrections. Now for moon, there is a problem again because you have that HP problem because it's close to the Earth, in which case you have to bother about the horizontal parallax. So there are correction tables given for moon, which are in two parts. One is your main correction. So when you go into the tables for total correction for moon, divided into two. One is on top, which is to do with only apparent altitude here, and the apparent altitudes are given here from 0 to 4 degrees and 0 degrees, 0 minutes, 10 minutes, 20, 30, 40, 50, and 1 degree. So whatever is your apparent altitude, you can get the values from here. If required, you can interpolate. Then comes the HP correction. The HP, as I said, you get it from the almanac. And then the second part of these tables, total correction tables, is your HP corrections, in which HP is given here on the sides. And in the same column of whatever your apparent altitude was there, you will get the value for HP correction, and this is for lower and upper limb. So depending upon what limb you have got, lower or upper limb, if your apparent altitude was, let's say, in this column of 15 degrees some minutes here, in the same column you continue down and look for the HP and get the value for upper and lower limb. Now all these corrections are to be added to the apparent altitude, but 30 minutes to be subtracted from the almanac, from the altitude what you have got. And this is also written down there in case you ever forget it. It's part of the tables there. This is mentioned there, so you can always consult your almanac in case you ever forget it. But very simple to remember that in case of upper meridian, upper limb, you always have to subtract 30. All are added, but in case of upper limb, subtract 30 minutes, and then you get your true altitude. So this makes life simpler than having to do all the individual corrections. As I said, that should be known to you. Sometimes can be asked as a principal question. I'll just give you an example here how to go about solving this thing on moon. I'm not talking about the moon, sun, and other things because moon is a little different. So I'm talking about moon here. The date has been given to me, GMT is given to me, it's upper limb, altitude is there, index error, and height of eye. So I write down the sextant altitude, index error, as I said, on or off the arc. Here it is on is subtract, I put minus sign here. And this is the value of my observed altitude. Next correction is height of eye correction. And as I said, it's always minus. We have these tables here. Again, in your almanacs, you'll find it even in your nautical tables. That's your Norries and other things. And here you get your height of eye correction. My altitude, my height of eye was 12. So 12 is here, between 11.8 and 12. So my correction is minus 6.1, 6.1. And then I've got apparent altitude. Now the bodies come onto my visible horizon, or you can say onto my sensible horizon. The next correction I apply is the refraction. Again, as I said, we get it from the tables here. Tables are there in your in your nautical tables there. My altitude was 56 somewhere here, and 0.7, 55, 60.7. So I've taken as 0.7. Then I apply semi-diameter. Now this day happens to be the second day on the page of this day here, 24th. It is this page is for 23rd, 24th, and 25th. So 25th, 24th is the middle day. So this is my semi-diameter for that particular day. So I've written down my semi-diameter here. But to this, we have to add augmentation. And augmentation, we get it again from the tables here. Always to be added. Now my semi-diameter 15.1, my apparent altitude 56 here, 0.2, always to be added. So now my semi-diameter has become 15.3. And this is what I will be applying here as semi-diameter 15.3, being upper limb subtracted. Now next is parallax. Parallax for moon is HP into cos of apparent altitude. I go into the date of 24th here. Time is 2300 hours. My HP 56.55.8. And with the apparent altitude into HP, I got my parallax 31.1, which again we said is always added, and that is my true altitude. This is how I'll do it if all the individual corrections had to be applied. But easier way is to use the total correction. So up to apparent altitude anyway we have to do, for either case we have to apply index error and the height of high correction. So we come to apparent altitude. Now the next correction what we apply is the main correction. We go on to the page where we have apparent altitude is 56 degrees. Here, this is 56 here, and 7 minutes comes in line with this. So my main correction is 42.1. An HP correction on the date of 25th, my HP was 55.8. On the same column where I saw my main correction, I go down here. Upper limb, my HP is 55.8. Wherever they meet, upper limb is 3.1. So the mean correction is 3.1. Now we just saw that all the corrections have to be added up and 30 is to be subtracted from here. So I add up all of them, subtract 30, and this is my true altitude. So you can see that the true altitude either way is nearly the same. But this is definitely faster. But as I said, a candidate is to be aware of all these individual corrections here. Thank you. We'll continue with the calculation of time for meridian passage.